In this example, we're given a circuit that contains one capacitor in here, and we are also being told that initially this capacitor is uncharged. And it has this switch in here, and what we are being told is at t equals 0, the switch goes from A to B. Basically, it stays for a very long time uncharged in A, and then at t equals 0, what happens becomes at B. And of course, in that particular case, you might have seen it or recognize it by now that this is basically just a step response of an RC circuit. And then after 15 milliseconds, what happens, like the switch goes from B and it goes to C, okay? And of course at C, you're left with this circuit in here, which is just simply a natural response of this RC circuit. So whatever the 400, whatever charge the 400 volt gave to that 0.1 microfarads will basically start giving it off to the 50 kilo ohms. And what we're being asked to compute is this voltage across this capacitor, and also we can also sketch it. All right, so how do we go about this? Well, we can, of course, we have a step response initially and then natural response. You can look up these equations, or we can just simply say, well, we know the general solution for first order transient circuit looks like that. And what we have is we have two of them because we have two switches. This is sequential switching in here. So let's go with that. So what I will do is I'll say, well, okay, let's find the initial value in here. So we're going to start with the very first one, which is basically from t is greater than 0 and less than or equal to 15 millisecond. And I believe it's 15 milliseconds. Yeah, milliseconds correct, not seconds. Okay, so 0 to 15 millisecond, that's perfectly fine. So what we need to do, of course, the thing that we're targeting, x, should be just simply v of c. That's what we have. You can substitute it. So what do we need to do? Well, the initial, okay, so let's do initial in here. So in terms of initial, what we have is the following. V, C at exactly 0 minus, which is 0 plus, which is actually just simply 0. Okay, we know because we're given that it's 0 volts in here, because it tells us that initially it's been uncharged. So there's no energy stored in that capacitor. So that makes our life a little bit easier. Then what happens next? Well, what happens next is at t equals 0, so that's here. I'm going to do the final, okay? So at t equals 0, what happens, like that switch becomes, instead of A, it goes to B. So what we're left with is the following. Let me just clean it up here. So what you will see is the following. You'll see something like that, okay? And of course, no resistor in here, because this resistor is still not connected. So that's what we have, and what we need to do is we need to do VC final. I'm going to call it VC final 0 because this is the very first VC final. And you might have recognized that really all you have to do is put here, this becomes an open circuit, and what we're after is here plus minus VC final 0. And of course, if this is an open circuit, this is simply 400 volts. Okay, so that becomes here as 400 volts. That's what we have. Okay, and what about tau? Well, let's find tau, which is, I think it's R equivalent 0 times C, okay? And the R equivalent is simply here, okay? So this is the R equivalent, which is the R Thevenin, which I don't need to compute anything. It's basically whatever that capacitor sees in here, and the capacitor only sees this 100 kilo ohms. So that becomes 100 kilo ohms in here. Okay, of course, that means tau, I'm going to call this 0. Tau 0 is just simply 100 times 10 to the power 3 times, well, how many? It's 0.1 microfarad, so it's 0.1 times 10 to the negative 6, and that value is simply 1 divided by 100. That means 1 divided by tau 0, well, this is in second. 1 divided by that is 100 second to the minus 1. And I think we have everything we need to do in order for us to figure out the first value for VC of t. And that's, of course, for t between 0 to 15. So this is t here. It's between 0 to 15 milliseconds. And that basically tells me, well, all you have to do is just substitute. What's the final value? The final value is just 400 plus the initial value was 0 minus 400 e to the negative, I believe it should be 100 t minus t0, because that's the initial switch in here. So we clean it up. VC of t equals just simply 400 minus 400 e to the negative 100 t, and that's basically amps, or actually this is volts, for t is between 0 and 15 milliseconds. So let me just do that here, okay, and just highlight it so that we could refer to it back if we needed to. All right, so this is right before we switch from B to C. So at 15 milliseconds, we go from B all the way to C. So let's draw that circuit here. And what we'll end up with is the following. We'll end up with this circuit in here, okay? And again, what we have is, well, we don't have A anymore. Okay, we don't have this part of the circuit anymore. We remove it. Okay, we don't have the A anymore. So what we're left with is just simply this case in here. All right, so in this particular case, we need to figure out again, we need to figure out the initial, the final, and so forth. So what we need to do is, let's do the initial. So what's the initial at this particular state? Well, the initial is simply VC evaluated at exactly 15 milliseconds. Times 10 to the negative 3. Well, how do we compute this? Well, as it turns out, that because the voltage doesn't change with the switching in here, well, it doesn't change at like exactly at 15, right before 15, right after 15 is the same, we can just basically use this equation to compute it. So that becomes 400 minus 400 e to the negative 100, and now the t is just simply 15 times 10 to the negative 3, because this t here is expected to be in second, because this is second minus 1, so I converted this to second. And the value would be, I believe it should be, I'm going to approximate it, it's about 310.75 volts. That's basically the initial voltage across that capacitor. And then what do we need? Well, we need the final, and hopefully you can recognize that the final in this particular case will be just, I mean, I don't have to redraw that circuit, because the final VC final 1 will be just simply 0, because what happens is it will give all this energy, this will consume that energy, and that's it. If we wait for a very long time, that's what would happen. And now what we need to do is we need to find tau, okay? So tau 1, for example, which is the R equivalent 1 times C, and in this particular case, tau 1, the time constant, the R equivalent happened to be 50 kilo ohms, okay, negative 3, or actually plus 3 here, 50 kilo ohms times 0.1 times 10 to the negative 6, and that equals to 1 divided by 200, that's in second, that means 1 divided by tau 1 is just simply 200 second minus 1. And I believe we have everything we need to actually write this equation. So what we need to do is we need to say, well, for t is greater than 15 milliseconds, what we happen is VC of t is just simply, well, what is the final value? The final value is 0 plus the initial value, which happened to be that 310.75 minus the final value, e to the negative, this time it will be 200, but t minus 15 times 10 to the, this is 15 milliseconds, so negative 3 in here, okay? And that here becomes VC of t is just simply 310.75 e to the negative 200 t minus 15 times 10 to the negative 3, and that's here in volt for t is exactly greater than or equal to 15 milliseconds. So we'll highlight this, and I think we have everything we need to actually sketch how this voltage across that capacitor does. These are the two ping thing in here. So if I combine these two pings, this is how it will look like. So between 0 to 15, we have this particular function or equation that describes the VC of t, and after that, this is how it looks like. So if we want to sketch it, that will become something similar to this. So we have the t-axis, we're going to start at t is exactly 0 in here. That will be VC of t, okay? And what we have is initially, the initial voltage happened to be initially at 0, because remember the capacitor was not charged. And then what happened is we'll see that the final value in here, and you can take a look at this equation in here. You can substitute this to be 0. If you do, the whole thing in here, the e to the power becomes a 1. 400 minus 400 is just simply 0. Right after switching, we cannot jump. So what we do is we slowly reach the final value. What is that final value? Well, technically, if you look at this and you substitute this to be infinity, so the whole thing here becomes 0. So the final value that we're trying to reach is 400. Okay, and it will take basically, it will try to reach it, but it never does actually. And what happens, like what it will do is it will actually reach the value 310.75. Okay, and I think I have like a little type on here, not 7.5, it's just 7.5, 310.75. Okay. So we have that, and then what happens at that particular moment? Well, at that particular moment, we have the second switch in here. So the second switch in here at exactly 15 millisecond, okay? What happens is like we we switch to a different case. Remember this here. So what we did is we were initially from A to B. We were trying to reach the 400. We never do, because what we do is we don't wait enough. Because at 15 millisecond, we basically switch to C. So what happens is like that 400. Before reaching the 400, we reach 310, and what happens is we basically try to get to 0. That's what we try to get. That's basically what you see in here, because the final value, if you substitute t equals infinity, you'll see the whole thing goes to 0, and that's how this looks like, and this here is time.